All right, so I'm going to start a new list of people who have questions. So we have a topic for our panel discussion, which is something about...
I can read it, actually.
Yeah, something about effective field theories, I bet.
What are the reasons for adopting an effective field theory point of view? What impact does this have on interpreting QFT? So we've had several answers to these questions already, I think, but and I should say I'm the guilty party in terms of formulating these questions. Hopefully it might be a useful launching off point.
Okay, so...
Maybe I'll start with just elaborating a little bit. Is that okay?
Sure.
So I think there was part of the discussion after Mike's talk, which was very useful in directly addressing this. One is just, shouldn't we have always been thinking in terms of effective field theory? And in some sense, maybe we were. Just in the sense of being modest about what our theories say about extrapolations beyond the regimes where they've been tested, but that the effective field theory techniques add a very specific contentful way of saying what those limits of the domains of applicability are, and give us a much better grip on how things break down as we go to different scales and what those sorts of transformation properties look like. So that we might have initially had a very loose sense of we should be effective realists or we should adopt an effective field theory point of view, but there's now something that's much richer that we've discovered in the physics. And I'd be curious whether people think that's right or if it's actually that there's something quite different that's going on with the development of an effective field theory approach. I can see David wants to. Yeah.
David.
Yeah. I mean, I think picking up on that, I think there were various comments in the literature as well about the fact that we should all have an effective take on theories and shouldn't think about theories as fundamental, and I'm very sympathetic to all of that. But I do think it's important to hold on to the fact that in the specific context of QFT, we have a comparably specific notion in play, and there's a lot that follows from the fact that QFTs are effective field theories that isn't just a special case of what follows from the fact that any of our physics theories are effective theories. I mean, it's a fact about effective field theories in QFT that they are described by quite a small number of parameters. They display high levels of insensitivity to high-energy physics. Didn't need to work that way. There are physical systems that don't work that way. Turbulence doesn't work that way. Yeah. QFT does work that way. And I think while I think it's great that philosophy, physics and science is thinking more about theories in a non-cosmological, non-fundamental way, I hope we don't lose track of the fact that there are quite specific effective field theory things that will come out from particularities of QFT that won't just be part of that general framework.
Good, and if I could pick up on one thing that you said that is also quite interesting.
Alex wanted to add something.
Go ahead.
Okay, so
this is a new thing.
Yeah, so, and that's just, there are any cases where you have like an inverse energy cascade or turbulence, you won't have the kind of separation of scales that are characteristic of effective field theory techniques. So it is, I think, important to acknowledge that maybe we shouldn't say the detailed sense of effective field theory applies across the board either. So I totally accept that. I think that's one thing that is very interesting in considering cases like quantum gravity and cosmology. Are there limits of the effective field theory techniques, and how could we characterize those?
Alex.
Yes, okay. So I've been thinking all day about what to say here because I thought we were going to be put on the spot as speakers again, as yesterday's speakers were. But so I have to get it off my chest now because I thought up something about like a point as the historian and devil's advocate about the reasons for adopting the effective field theory viewpoint as in the question for the panel discussion. And I think that, I mean, there's a bit of a paradox, which we've been talking about before in the break, right? In that the rise of the effective field theory view historically happens in the course of the 1970s, early 1980s, at the point where we actually, for the first time, have a model of a quantum field theory that might not need to be an effective field theory, namely QCD, and at the point where we actually obtain the very theory that has now lasted for 50 years, the standard model, even though there are reasons to believe that that has to be an effective field theory, still it did form a kind of completion there. And so I was wondering about that, and I think that there is, and I haven't done any historical study of this, obviously, so this is just conjectural, but there is, of course, a sense in which the effective field theory point of view is attractive to physicists, not just like on a philosophical level of how much should we trust our theories, but for the narrative that it gives for the future of high energy physics. Because it really gives you the story of, oh, our theories are all effective field theories. There is an endless frontier of new energy levels and new effective field theories to be explored all the way up to the Planck scale. And that's a very, very attractive story because it really like sets out the story for high energy physics for the next few centuries, right? We're just going to build one accelerator after the other and uncover the next level of effective field theory rather than having to face the depressing desert that David was talking about. And so I think we should not lose track of the attractiveness of this view to physicists for that reason that I think is independent of like the philosophical reflection on, you know, how modest it's in a way it's the opposite of, we've been talking a lot about the modesty of the effective field theory view, but there is a certain immodesty involved there in that it really at least implicitly endorses this view of an infinite onion of layers that we will be able to discover with accelerator after accelerator. Yeah, just wanted to make that point.
There seems to be a sting in the tail of that scorpion, though, because if there's decoupling, even though there's an onion of energy scales that you might look at, it gets harder and harder to use what is accessible to say anything about the further layers of the onion.
Well, I think there is. I mean, you do have at the very end of that onion, you have quantum gravity, and so there is there's a story of like slowly like following like a trail of breadcrumbs that will lead you to quantum gravity, which is not entirely decoupled because we see gravity at macroscopic scales. So we do have something that's accessible at the very end, and I think that very idea of following the breadcrumbs toward a theory of quantum gravity is precisely what supersymmetry and its connection to string theory was supposed to do.
David?
Yeah, I mean, just as a possible worry about that historical narrative, I appreciate it. You're not claiming that's somebody's fault, it's exploring. I mean, my sense of 1980s particle physics is it's very unificatory and very one-off. I mean, you have string theory getting attractive, you have a lot of people playing around with grand unified theories, you have Wilczek extrapolating the electric and weak and strong coupling constants and finding them with supersymmetry they exactly cross around that. You have a gut scale being floated around there. It doesn't feel to me as if the centre of gravity of what people were thinking about in the post-standard model period was as incremental as that model would suggest.
I think that's probably true. I mean, I think that the motivations may well have changed over time. I think that may have been a narrative that was more strongly adopted, say, in the lead up then to certain accelerator projects. But yeah, as you said, I'm just like putting that out there. I would maybe do research on it someday, but I have not.
I like the idea of putting the other speakers on the spot, actually, if they've all done their homework like Alex has.
Okay, I see Adam has his hand raised anyway.
So not being put on the spot because I want to contribute to this, so maybe give me a few more minutes. I think there's an interesting sort of contrast here. So regardless of whether that's a compelling historical narrative or not, I think there's an interesting point between what can effective field theory do for us if we're trying to investigate and explore the world versus the questions that Mike was bringing up about which seem to pull in the other direction. If we should, pulling us towards modesty of what we should be committed to in the world, and I think that's a good and important point. But then, on the other hand, this more specific framework of effective field theories as they come up in quantum field theory give you a set of specific tools to think about scaling behaviors. They give you, it hasn't panned out, but they're supposed to give you insight into where those theories break down, like the Higgs mass and the cosmological constant should have, under normal expectations, should have told us where we expected the current description of the standard model to break down. So there's interesting tension between, as philosophers, we want to be modest realists about certain things, but then methodologically we also want to use the tools we have to extrapolate and to learn about new physics. This comes back to something, a point Wayne made, but I almost wanted to draw the opposite conclusion. So Newton's rule 4, he's cautious of until we have reason to think otherwise, but he also says we should extrapolate as far as we possibly can until we have reason to think otherwise. And there does seem to be a methodological tension there between saying our theories we should, even if their theories don't explicitly tell us where they break down, we should be cautious and expect them to break down somewhere. They're not irreconcilable, but there is sort of a tension between we're only committed to these things, but yet methodologically we want to push well beyond those.
James, I'm going to put you on the spot then.
Okay, fair enough. I haven't really done my homework. But I guess, I don't know whether it's interesting to everyone else, but me and Mike could talk about whether we do actually disagree on anything or not. Since that was
Actually, I was going to ask you that,
raised
if
as
you
a-
wanted to disagree with anything Mike said in his talk.
I don't think very much, to be honest. I'll maybe say something about each of the two questions. So that the first question was, what are the reasons for adopting an effective field theory perspective? I mean, there's kind of I guess there's a question before that of what an effective field theory perspective is, which I may just leave for now. But yeah, so there were three, I think for me, there seemed to be three different kinds of reasons, potentially, that were all things that Mike talked about. So on the one hand, there's kind of potential internal conflicts within quantum field theory itself. So these kind of inconsistency worries that Alex was talking about and has been working on recently. And there's loads to say there, obviously. I mean, the internal problems of quantum field theory are very complex, and what kind of weight we should put to different issues is a very complex issue, a very complex question. Then there's the kind of external conflicts, so like conflict between QFT and gravitational physics, say, has been thought of as another reason to adopt some kind of effective field theory perspective. But one thing I definitely agreed with what Mike was saying was the third kind of argument, which is this like scale separation argument, is for me like the most interesting and important reason for adopting an effective field theory perspective. The other two, like, there's lots to say there, but in some sense, I think the scale separation argument kind of should be the master argument for adopting some kind of effective field theory perspective. So I think we agree on that point. But then the second question is, what's the implications? And one thing I did want to raise, which did come up in what Mike was saying, and we've talked about this a few times, and this kind of comes back to the question of what is an effective, what does it mean to adopt an effective field theory perspective? Because there's potentially different ways of thinking about what you're doing when you adopt an effective field theory perspective. In particular, you could distinguish between a more semantic move and an epistemological stance towards a theory. So basically, the epistemological stance would be, not committing yourself to certain claims made by the theory, specifically kind of what the quantum field theory is saying about the fundamental or the shortest possible length scales described. And then a more semantic view would be to say, well, we shouldn't really understand quantum field theories as making claims about the fundamental in the first place. So it shouldn't even really be understood as part of the content of a quantum field theory to be making claims about, say, arbitrarily short length scales, or even if we're talking about a lattice framework or something, that we shouldn't understand the theory as kind of actually attributing a lattice structure to the world. And I think this is in the papers that me and Porter wrote about this effective realism idea. This is a bit of a difference between me and Porter. Porter actually, even though he talks about selective realism and Silos and so on, the program that he advocates is actually not very closely related to that, I would say, because he's really arguing that we need to change the way that we interpret physical theory, and that's really phrased as like semantic project, that we need to change the way that we're thinking about interpretation, move away from these approaches to interpretation which identify the physical content with what the theory says about the fundamental. And in my papers, I phrased everything in a much more epistemological way. And I guess that's because I tend to not have as strong intuitions about semantics. Like I tend to have a more, I'm quite like epistemological orientated person in that respect. And for me, as long as you have some kind of view of theory semantics which allows you to give meaning to the non-fundamental stuff which we want to commit ourselves to, then I'm kind of fine with that. So it's not obvious to me that like this sort of standard account of interpretation that Porter really doesn't like, the sort of possible world semantics, where you view the content of a physical theory as being given by a class of possible worlds. I'm not really advocating that view, but if within that kind of approach you can still give some kind of meaning to the non-fundamental, like low energy content of the theory, then that would be fine with me. Whereas I think Mike is more kind of tempted by more revisionary sort of semantic projects. So yeah, that's potentially one difference between us, which we have talked about a few times, but maybe other people might have thoughts on this.
David has a finger.
I don't know. Oh, I was going to say, and maybe this is a broader theme as well, but it came up in James' comment. I find it slightly strange that we have this conversation as if it would be optional to take an effective field theory perspective, and then we consider the desiderata. I mean, what's the alternative? I mean, we know, even leaving aside number normalizable terms or Landau poles, I mean, we know from effective field theory that the long-distance physics is completely insensitive to how the short-distance physics is filled in. So the alternative to having an effective field theory take is just to fill in the short-distance physics in whatever way we feel like and just pretend it's true. I mean, even if we had, in the maximally friendly position for non-effective field theory, suppose we win the Clay Prize and get an ultraviolet completion of quantum chromodynamics, still, why explore that theory rather than lattice gauge theory? I mean, there's no reason to think that neither of them is true. Neither of them have the right short distance physics, we know that for a fact. It might be pragmatically convenient to use one of them for one purpose. And maybe if we have a taste for fiction of the kind whose plot and characterization Wayne disdains, then maybe we'd like to explore the fiction that our Clay Prize winning QCD is actually the exact truth. But yeah, maybe we want to explore the fiction that lattice gauge theory is the exact truth. I mean, I'm very permissive in my taste for fiction. What beyond playing fictional games? I mean, what actual alternative would be on the table to saying we should be effective field theorists, even about QCD?
I have a finger on that, but I mean, I largely agree, and I think that one of the things I find compelling for reasons to so external reasons of pursuing like quantum gravity or something to go beyond effective field theory. So again, this comes back to what James said, that it depends on what you mean by an effective field theory perspective, but it also seems that our current best theories are even less sensitive to high energy physics than we might have expected given effective field theory methods. So again, I come back to the Higgs mass and the cosmological constant problems, where if you include your normalization group and scaling behavior and step into what you take the effective field theory perspective to be, and you don't even have to subscribe to that much naturalness, you just have to assume that there's not really, really delicate fine-tuning. We should be seeing new physics much earlier than we are. And so there's an interesting point where there's sort of and David, you've talked about this as like a sort of anomaly for the perspective, but it's in some sense interesting that our current best theories say that there's even more of a separation of scales, even more insensitivity to high energy physics than we should expect, given that we adopt an effective field theory perspective.
Alex.
Yeah, I think what I wanted to say goes along similar lines and goes along. I mean, I think one can at least distinguish two kind of effective field theory views, and one is indeed without alternative. We know that we somehow need to incorporate gravity and so we really have no alternative to saying, oh, the standard model as we have it can't be. But I think that's not really what people mean. Or when they say effective field theory view, because that's just there's an actual phenomenon that we have not yet integrated into our model building. While the effective field theory view, there's another one that seems to say that even if there are no phenomena, right, that somehow are point that I need to integrate or point in a different direction, even then I should be forced to assume that what I have is just an effective field theory, and that I should only be trusted in that certain domain. So I think that really one needs to distinguish between those kind of two effective field theory viewpoints, namely the one explaining how we can even think about the standard model in relation to gravity and how we should think about that on the one hand, and on the other, totally separated from that, the assumption that we should, any quantum field theory we have, no matter the other empirical input, we should always only trust it in this. And even if we have like a theory of quantum gravity and have no other, and that turns out to be just some sort of asymptotically safe quantum field theory, then we should still only trust that. And like say, there are still there might still be trans-Planckian mysteries out there. Even though we will never see them, right, we still need to have an effective field theory viewpoint. And I think those are two very distinct standpoints.
I'm going to let...
That's fine. Just because I have to think about doesn't mean you take a question.
Oh, sorry, did you see?
I totally, yes,
Okay.
Yeah.
So I completely agree, and I think it's important to isolate the kinds of reasons that are getting offered in both of those cases. And so for me, what's pressing and what makes me say the second thing, which I agree is different, is just that I worry about trusting theories and regimes where we don't have direct empirical contact with the kinds of things that the theory says, and yeah, that's not a particularly that's a commitment coming from probably background. That's a background commitment, not necessarily attached directly to anything having to do with effective field theory in particular, but rather with the way that I think about empirical support for theories and that kind of issue. And so that's not an EFT particular kind of claim. That's a claim about theories and evidence and that kind of thing.
Did you want to say more, Mike?
There was like a few.
Okay.
Let's just no. I think this is a productive line, so let's keep going on this.
Yeah, I think these quantum gravity issues come a bit closer together than it looks. I mean, I think it's not that we can't incorporate gravity into the standard model. We can do it fine, but it's non-normalizable. So it tells us there's an energy breakdown in the Planck scale. So I think the reason we should think about special relativity, about standard model as an effective field theory in that sense, isn't just generically because we know left out gravity, it's because of that non-normalizable interaction term. And then if we did have if we do try to do quantum gravity on Planckian or sub-Planckian scales, I think we have a breakdown of the particle physics paradigm at that scale. I mean, at the Planck scale, the short shield radius is larger than the Compton wavelength. the Planck's, if you try colliding together particles that are heavy, elementary particles that are heavy in the Planck scale, you just get black holes. The radiation that comes out of them is going to be lower than Planck scale. If I try thinking in terms of the larger and larger k values that I use to parameterize field theories, the kind of this is approximately free particles interacting frame that completely breaks down at that scale for gravitational reasons. So in terms of the terminology that came up earlier in Chris and my comments, I can perfectly well believe that even our perfect quantum theory of gravity, we might want to think about as an effective theory, but I don't think we'll want to think of it as an effective field theory, because the scale dependence, I don't think that's incompatible with anything I might be saying, the sort of specific way in which effective field theory works will have failed, will stop working beyond the Planck scale.
Okay, go ahead.
This is a new topic, but I thought Marco's question was really interesting and that I had nothing helpful to say about it, and I'm curious if anyone else does. So, I don't know, Marco, do you want to say again what you were curious about?
Yeah, so you said that, did you speak up? Oh, yes, sorry. So we have this effective realism approach, and I was wondering if that would be the best attitude to have also with respect to cosmological theories that make claims about the extremely far future, given that we cannot have empirical access to that future.
I could add something very briefly. I mean, I think the main question the contemporary cosmology poses but doesn't have a clear answer to is what is the nature of the dark energy? And the assumption is that because that doesn't dilute with expansion like everything else, the far future of the universe will depend. I mean, so if the dark energy dynamically evolves in some way, then you could imagine it changing over time. So far, it just looks like a cosmological constant, in which case the far future would just be essentially approaching de Sitter, and you can have some kind of convergence results that would say all of the other matter and energy density would be diluted away, whereas the dark energy will remain roughly constant. But there again, it's sort of the extrapolation you're making is assuming that you understand the dynamics of dark energy well enough to make this extrapolation to enormous distance scales, time scales. But I think that's a different kind of issue than the kinds of issues we're facing in effective field theory. So I liked your question, but I didn't really, beyond that, I didn't have much to say.
Bill, this is just a follow-up. In a certain sense, I would presume that the dark energy is more or less a phenomenon, but we don't yet have anything like a real explanation. Is that fair?
I mean, in some sense, it's depressingly well fit by just treating it as a cosmological constant. And cosmologists are frustrated by the fact that they haven't been able to find departures from that. And the departures would maybe help you to see if there's some underlying dynamics.
That might explain why if it's a constant, it's 10 to the power of 100 smaller than it's supposed to be.
Yeah, that's the other issue. Yeah.
Yeah, so it's not a direct answer to this question because I agree that I think it's an interesting question, but I don't have a good answer. But so Chris and I have thought a little bit about thinking about like gravity as an effective field theory and problems with infrared extrapolation. So this isn't necessarily time scales, but large distance scales. And I think this kind of goes with some of the things I was gesturing to towards the end of my talk. If we think that we apply especially effective field theory methods to sort of local, well-behaved regions of spacetime where we can set up even an ocean of energy scale and then separation of those scales, we can Fourier transform and go between momentum and energy. When you try to then extrapolate what you learn about local physics to the largest distance scales in the universe, there's a lot of room. I mean, we don't have good like exactly good theoretical arguments for these things breaking down, but there's also a lot of room for those things to break down. So when we preach sort of modesty in the extreme UV, I think it's also clear that we should maybe preach that same modesty in the extreme infrared as well. That's not to say that things won't apply or that we can't make predictions like that, but I just think that if we're going to have that sort of scale-dependent modesty, there's at least maybe not as compelling, but I find compelling reasons to distrust what an effective field theory treatment would give you if you're really extrapolating globally.
Well, I mean, here's a response to that, and then here's a response to the response. I mean, in a sense, there's a very good reason in effective field theory why we trust the IR and not the UV, which is if we go to the UV, any number of irrelevant terms might turn up and swamp us. On the other hand, if we go to the IR, any relevant terms should swamp us, and they don't. So that's the reason to think you're probably right, because that general argument isn't working properly in that case.
I was curious to come back to the semantic question that James posed to Mike.
That was the other thing I was going to circle back to. Yeah, so I think again that's something where we differ, but again on grounds probably external to effective field theory in particular. I think that might just reflect my own kind of perhaps anachronistic views about how physical content attaches to mathematically expressed physical theories, independent of whether they happen to be effective field theories or something like that. And so, yeah, I've been personally very compelled by the kind of Mark Wilson line about these sorts of questions. And I think if you're thinking in that kind of way about how physical content gets into mathematically expressed theories, then and then you read effective field theory, it starts to look very natural to make these to advocate in favor of these sort of semantic reform kind of mechanisms. What shape exactly that's supposed to take, and to like how revisionary one wants to be. I think there's lots of space for different kinds of views, and I don't feel like I've got a fully articulated view or anything like that. But yeah, I am. It makes me a little hesitant to think that I don't like views where you talk yourself into thinking that the conditions for having to be able to say something true using your physical theory require that what you've got is this complete, exhaustive, fundamental mathematical characterization of reality. I think if you do that, something has gone wrong. And I see the semantic reform, if you even want to call it that, just as a way to take seriously that the kinds of claims about the world that the standard model delivers us on the scales where we think it's empirically trustworthy are as good as the claims that a physical theory can get us, and that they're similar in kind to the nature of the theories that came before, which we now recognize to be non-fundamental. And okay, the effective field theory picture tells us that that's going to be the fate, or very likely to be the fate of the standard model as well, contemporary physics as well. And yeah, it just starts to sound really funny to me to say that we can't say true things with our theories without having achieved something that we just don't know that we'll ever be able to achieve.
Alex, go ahead.
Oh, does somebody want to directly respond to this?
I'll think more.
I'd like to talk something else.
Go ahead, James.
Okay. I'm getting a bit confused now because we've been moving between a few different topics, and I've had something I wanted to say about each of them, so now my brain is like full of many different things. Yeah, I don't think I have anything yeah, I kind of want to come back to the question of which Alex raised of the difference between kind of take the very uncontroversial effective field theory stance that David was pointing out, that, you know, we don't have fundamental theories, so, you know, that nobody can really, you know, there's not much you can do about that philosophically. Like, that's definitely true, but Alex, you were sort of suggesting that there is a more radical claim, which is not just a claim about our current epistemic situation, but somehow a projection about what is possible knowledge, not just what's current knowledge. And Mike, you made the point that your reason for maybe holding this more in principle claim, that, you know, it's not just that we don't currently know about arbitrarily short length scales, but that's like not a possible object of knowledge, was kind of coming from the fact that those regimes are not ever going to be, they're not possible objects of observation. But that's actually quite so I was just going to say there's definitely another component to that, because you could imagine if scale, you need scale separation in the picture, I think, in order to really have an epistemological worry here. If you didn't have some kind of separation of scales, you could indirectly confer, you know, like observations made at some finite scale could, you know, conceivably like single out a unique ultraviolet theory, extreme ultraviolet theory. So it's only when you add scale separation in that you get a kind of in principle worry there. And I think that's actually why, when I was saying that there's three reasons to adopt an effective field theory perspective, and the scale separation one's the most interesting, because the other two just seem to be contingent on our current state of, you know, so there's internal conflict within quantum field theory, but we can imagine that could go away in a future theory. And there's conflict between different areas of physics, but, you know, a unification project is going to get rid of that. So the only one of the three that might be kind of not just transitory, but kind of a permanent feature of our epistemic situation would be the scale separation argument. But then there is a question of whether that really will be permanent, and I guess yeah, Adam and Chris's paper on UV-IR coupling duality kind of raises that question of whether scale separation is, well, you were also raising that question earlier of kind of how general scale separation is, because there are obviously cases where it's violated. So yeah, that seems like what you need to press on with in order to address this kind of more in principle question of what the limits of knowledge could be.
Yes, okay. This may be picking up on some stuff said earlier, maybe a little bit less emphatic. I was thinking, because it came up several times, like what would it mean if we were not to adopt an effective field theory standpoint, for example, you know, and so I think there is of course a long tradition. I've worked on John Wheeler and his program of Daring Conservatism, which is specifically about aggressively taking theories far beyond the domain in which they've been empirically confirmed and seeing what that would tell us, right? And Wheeler, with this program, you know, applying that to GR, achieved substantial results on stellar collapse and cosmology, and also gravitational waves, long before those things came into the domain in which general relativity was empirically confirmed, and he very, you know, aggressively promoted that as a program. but it was attractive in that case also because assuming that the theory has a far wider validity than we have grounds to believe actually gave lots of interesting problems to solve and tackle with it. And it seems that in contrast to that, assuming that the standard model is valid to the Planck scale, say, doesn't really give us anything to do. It's, as David said, it's a very boring proposition. There are no problems to be solved by making that assumption, except for maybe trying to see how we can get our way out of the hierarchy problem, but people seem to think that we have to do that anyway, given the results of the LHC. So it just, I'm not entirely sure why that is, whether that is like the flip side of scale separation, but I mean, I think, because this also came up this morning, right, the question of what kind of problems are we solving, it seems that a reason to adopt the effective field theory view, which is maybe like somewhat less, I don't know, sinister than what I said in my first comment, is really that if we just assume the standard model is fine until the Planck scale, then all we can do is maybe like play around with quantum gravity, but otherwise there's nothing left to do in quantum field theory.
Mike?
Just one brief clarification. So as a methodological matter, I think it's great to execute that sort of exploration of what happens to a theory if you extend it far beyond the regime of it's the kind of empirical support that enjoys. I don't intend to be discouraging people from doing that, quite the contrary, that's important. It's just when it comes to when I want to now engage in this, what I regard as a slightly distinct activity, which is given the kinds of empirical information, or the kind of, let's say, the kind of success that our theory enjoys, whether that's explanatory, empirical, whatever it is, what kind of picture of the world am I warranted in being committed to? And it's there where this kind of stricture to not get out in front of the empirical support, I think, at least for me, kicks in and becomes quite important.
David and Eva.
I mean, let me give a slightly, it's in some ways more optimistic, in some ways much more worried version of Alex's gloss. I think prior to 2010 or so, I think what we would say is, well, the general rules of effective field theory say that if there's a scalar field, then the cutoff at which that effective field theory fails will have to be not very much above the energy of that scalar field. So we're going to find new physics that isn't just a scalar Higgs boson. And maybe that new physics is, say supersymmetric multiplets, and then that's it, we find them all, and now it really is plain sailing to the Planck scale, and in certain sense that's boring, but there's a last spurt of really cool particle physics before that. That didn't happen, but the fact it didn't happen doesn't tell us what went wrong with those arguments. I mean, the failure to find new physics above the scale of a fundamental scalar is a kind of thing to keep you awake at night. There is something badly broken in our understanding of effective field theory, and we don't remotely know what that is yet. I mean, the boring possibility is it's anthropic. It might be anthropic, but that's I think even as an Everettian, I could say I think that's a last resort way of thinking about it. This is I mentioned, as Anna mentioned this in way I before. This is an anomaly in Kuhn's sense. There's something really missing in our picture of what's happening in the effective field theory story.
Yeah, I wanted to build. So I completely agree with David said, but I'm going a slightly different direction. Building off the what Alex said about other reasons for adopting an effective field theory approach is sort of otherwise things would be boring. In a sort of structured way too, thinking about the standard model as an effective field theory gives you, I mean, and not very constrained. There's a lot of free parameters when you start going to above the renormalizable terms in the standard model. But it gives you at least some sort of structure for searching for new physics. We expect, we do parameter fits. We think that, the bottom quark, I think, is one of the areas where the non-renormalizable terms are not very tightly constrained. So we expect that, if the standard model is an effective field theory, it will have non-renormalizable terms that will crop up at certain energy scales, and we can then go kind of systematically look for those. It's kind of boring, it's precision measurements, doesn't give you much insight, even if you find a term, into what that implies about new physics because of the scale separation.
But it gives you the scale that new physics would have.
Well,
That'd be great.
yeah, with enough, with enough, like after some time of making more than just the one measurement, yeah, you can get an idea of potentially new physics scales. So yeah, there is, to build off of this being methodologically a useful way to think about physics going forward, even in the absence of thinking, oh, the next theory is going to be another effective field theory, it at least gives you a way to structure searches for new physics and to turn these sort of precision tests that we like to kind of brandy about when we're telling people why quantum field theory is so cool. It also gives you another reason to keep pursuing those, because those minor discrepancies might end up being the only window kind of we have into new physics.
But there is something weird. I mean, I absolutely agree that that's a great strategy, but there's something funny about it, because it's not, I was about to say we have no idea what energy scale those non-normalizable terms are going to turn up. It could be like 10 to the 10 up. But even that's not true. We have a very good idea of what scale it is. They should be turning up right now and they're not. I don't think we, again, in Kuhnian fashion, I don't think we have any alternative but to continue running the effective field theory game of looking for the non-normalizable terms. It certainly beats trying to come up with a random theory and looking for it, but we do it with a heavy heart. Something's badly wrong with the theoretical basis we're using to do it.
So it's 6 o'clock. What kind of time frame do we have here, Chris?
I think we should round up for tonight. It's been a great day, but it's been a long day as well. And so we have dinner at 7. So let's thank all our speakers from today. It's been terrific.